Welcome to the video on nucleophilic acyl substitution. Specifically, we will be talking about carboxylic acids and derivatives. Remember, in this reaction, the nucleophile attacks the carbonyl and kicks electrons up onto the oxygen, creating this tetrahedral intermediate that has a negative oxygen. In the second step, because we have the leaving group, a pair of those electrons will kick back down, reforming the pi bond and kicking out the leaving group. So we end up with our nucleophile attached. Now recall that carboxylic acids are planar molecules, so we can have attack of the nucleophile come from either side. Also remember that they are capable of these strong hydrogen bonds, forming this cyclic dimer. And also remember that that proton is acidic on a carboxylic acid. Most of the reactions that I'm going to talk about on this video involve that nucleophilic acyl substitution that we just talked about, but here's the exception. So carboxylic acids can be reduced to a primary alcohol with lithium aluminum hydride. Remember, lithium aluminum hydride is a source of H-. Please note that sodium borohydride does not work with carboxylic acids. It turns out that this reaction is a little bit different than the typical H- attacking a carbonyl. That is because our starting material is acidic. And so in the first step, that lithium aluminum hydride is going to react with that proton, giving us this carboxylate ion. That goes on to react with this species right here, transferring a hydrogen onto the carbon that was the carbonyl carbon, as well as attaching the aluminum species onto the oxygen. Then we have this leaving group leave, and we regenerate our double bond, giving us the aldehyde intermediate. In the second step, we take H-, as previously discussed in the aldehyde chapter, because this is an aldehyde, and we reduce that one step further, giving us our primary alcohol. So this is one reaction that carboxylic acids can undergo that does not fall under the nucleophilic acyl substitution, but instead is a form of nucleophilic acyl addition. For the record, we can also use BH3 and THF to accomplish this reduction. Notice in that reduction reaction, we actually have a change in oxidation state of that carbon. We also go from an sp2 to an sp3 hybridized carbon. And so that change in oxidation state is different from the rest of the chapter, where we're going to be talking about taking a carboxylic acid into a carboxylic acid derivative where we have maintained the sp2 character of that carbon as well as the oxidation state. We have simply interchanged the group that is on the carbon. So I just wanted to remind you that if we have a good leaving group, this acyl substitution will happen. Remember, ketones and aldehydes, the carbon and the hydrogen cannot leave, so they will not leave. So these guys undergo addition, and we talked about that previously. But in the reactions where we can have the leaving group leave, we will get acyl substitution. And that's what this chapter is about. And here's the mechanism of that reaction: nucleophilic attack followed by loss of a leaving group. And remember, carbon and hydrogen are not used as leaving groups. So I'd like to introduce you to the typical carboxylic acid derivatives. They are the acid halide, the acid anhydride, the ester, and the amide. We also need to talk about the nitrile here because it actually fits into the same category. It turns out that a carboxylic acid derivative just needs to have 3 bonds to an electronegative atom, and nitrile fits that bill as well. If we talk about the reactivity of these derivatives, acid halides and acid anhydrides are very unstable. They're not commonly found in nature, and they're very reactive. And so we will see that we can use those very easily to interconvert between all of these molecules because they're so reactive. Esters and amides, however, are very abundant in nature, which means that they're more stable, right? If they stick around in nature. Proteins actually have these repeating amide linkages, and in biochemistry, you'll call those linkages peptide bonds. If you remember in lab, we did an esterification reaction. It's one of the only times that the organic lab actually smells good, when we made all those really nice smelling esters, pineapple, banana, and pear. I think banana was the favorite. And also the compound melatonin has a nice amide in there as well. So I just told you that acid chlorides or acid halides and acid anhydrides are unstable and very reactive. So we will find these at the top of our table in terms of reactivity. And then esters and amides are more stable, and so those are lower in reactivity and higher in stability. So the 4 primary factors that we have when we're talking about reactivity: induction, so is that carbonyl carbon activated and or stabilized by induction? Resonance, is that carbonyl carbon more stable or less stable because of resonance? Sterics, is there some big bulky group that's going to be in the way, blocking the nucleophilic attack? And quality of the leaving group. So if we have something that leaves very easily, that is going to be a much more reactive compound. Whereas we have a leaving group that's hesitant to leave and is happier while it's attached to that carbon, then that reaction is going to happen less quickly. So if we look at acid halides, we have induction. So this is highly electron withdrawing, which makes that even more positive, which is a plus in terms of reactivity. Chlorine also is an amazing leaving group. We remember that from the SN1, SN2 chapter, right? So chlorine is a good leaving group. And finally, resonance structures contribute to this being a reactive species as well. One of the resonance structures has a full out positive charge on that carbonyl carbon. There's an additional structure that puts a positive charge on the chlorine, which is really not that big of a contributor. Resonance does activate this compound as well. Acid halides are reactive. And if we look at the anhydrides, also we have a little bit of electron withdrawing nature there, so that's going to make that more reactive. So our leaving group here has nice resonance, which will make it very stable. And so we have a very reactive species here because the leaving group is stable on its own. If we get to esters, OR is not a typically good leaving group. We're going to have to maybe trick that to leave by protonating potentially. We do have a little bit of electron withdrawing. So it turns out that because this actually does have resonance, it makes this molecule more stable, so less reactive, whether it's reactive or not based on all of these factors combined. And finally, with the amide, that's a very stable bond, which we can actually say is a good thing because it holds all of our proteins together. So if this was an unstable bond, our proteins would be falling apart all over the place, which is not a good thing. However, in organic chemistry, because it's so stable, we have a harder time getting it to react. Turns out these amides are less reactive also because of resonance stabilization. This third resonance contributor is a major contributor, and it makes that carbon less electrophilic, so less reactive. NH2 by itself is an anion that is not stable, so that will not leave. We're going to absolutely need to trick that into leaving, and we'll play some games with tricking both the ester and the amide into reacting as we move through the chapter. But I just want to state that anything moving down this ladder of reactivity is easy. So that acid halide is going to react very easily to create any one of these compounds, and we'll see that in the next slide. And so here, let's talk about reactivity among the derivatives. I want to point out here that carboxylic acid sits right here in the corner of the chart. We can see that it is almost equal in reactivity with the ester. And so what happens here is that reaction is going to be in equilibrium as we go from the carboxylic acid to the ester. We'll use Le Chatelier's principle there to push that reaction in one direction or the other. But if we see that acyl chloride or any acyl halide actually can easily go to the carboxylic acid with just water. It can easily go to the anhydride, and in that case, our nucleophile is going to be the green piece. It can go to the ester, and again, our nucleophile is going to be the green piece. And it can go to the amide, and then again, our nucleophile is going to be the green piece here. We can easily take the acyl halide and bring it to any one of these other derivatives because it is so reactive. It's very straightforward. And the same, once we have the anhydride, it's going to be very easy to get to the carboxylic acid by just adding water. We can get to the ester by adding an alcohol, and we can get to the amide by adding an amine. Moving down the table is very straightforward, and we can just simply add the nucleophile we need. So esters, to get to the amide, we just add an amine. And then again, I told you that this is an equilibrium. And so to get to the carboxylic acid, we're going to play games using Le Chatelier. Now, when we talk about the amide, that's so stable that in order to get the amide to react, we have to move up the ladder. And as we move up the ladder in energy, we have to use special reagents that are going to make that reaction possible. It's not always a straightforward reaction. You know, I might use the word trick, but we have to be creative in getting that amide to go up the ladder, and getting that ester to go up the ladder, and in getting that anhydride to move up the ladder. We will walk through each one of these derivatives, and we will talk about how easy it is to move down the ladder, and then we will show you how to be creative to move up the ladder. In all cases, we will talk about how to make it and then how to use it. In lecture, we will talk about all of these transformations. And as always, here is the summary of all the reactions in this chapter to help you keep it straight. Okay, great. See you in class.